What's up everyone, welcome back. Patrick here, moving on to the next example, the next video. We got another trig limit. So we got the limit as x approaches 0, cos of 5x minus 1 over 7x squared. And like the previous examples up until this point, which I've assumed you've watched, I'm going to be using these results here to help us out within the process. So looking at this limit initially, first off, notice we can't make a direct substitution because if we plug in 0 for x, the denominator is going to be 0, so we can't be dividing by 0. Also notice the numerator is going to be 0 because we'll have cos of 0, which is 1, and then we'll have minus 1. So the numerator would be 0 as well, so we'd have a 0 over 0 format. So we're going to have to use a different strategy. Now, this limit is actually pretty tricky. The method that we're going to use to solve it, we haven't covered yet. It's going to be pretty unique, kind of new. But when you look at this initially, you would actually think that just from the format of this, that we're going to be using this property here, like we did in the previous example. Because notice that we have cos of an expression minus 1. And notice in this property, we have cos of an expression minus 1 as well. So just looking at this initially, you would think we're going to use this property, but in fact, we're not going to use it. And that's what makes this limit a little bit tricky and a little bit deceiving. So before showing you the correct method of how to do this, I'm actually going to first show you the incorrect way to do it. Because if you look at this again, you would think we're going to use that second property, and I'm going to show you the method or the partial method of trying to use that second property and then showing you at the end why that won't work. And then I'll show you the correct method. I think it's going to help you understand more of why we don't use that second property. But let's assume that we will. So what do we want to do? Well, we got cos of 5x cos of 5x in brackets minus 1. What we want to try to do is try to get that same expression in the denominator. So then we can do a change of variable and plug in that theta and then use that property. So what I'm going to do is I'm going to take this 7 and I'm actually going to split it up, this 7x squared, and I'm going to split it up into 7x times x. So we kind of see it a little better. And now what I'm going to do is I'm actually going to take out this 7, okay, that constant out of the limit. And then notice that to have that expression 5x in the denominator, I'm going to multiply this by 5 over 5. Like that. So I'm going to multiply the denominator by 5, which is what we want to do, but then we got to multiply the numerator by 5. So instead of just taking out the 7, I'm actually going to take out this 5 as well in the numerator because we're within the limit, we're only going to be using this 5 here to connect with one of the x's. So if I take out a 5 over 7, what we'll have is the limit as x approaches 0 of cos of 5x minus 1. All over this 5, I'm going to combine with this x here. And then I'll be left with another x. So I'll just put 1 over x like that. Right? So notice that we just kind of mix and match this. This 5 and this 7 we took out. This cos of 5x minus 1 I put over this 5 and 1 of the x's, and then there's still that other x remaining, so I made its own. I made another expression with it, 1 over x, like that. And then from here, what we can do is we can rewrite the constant, and then we can do limit laws. So I would make this into 2 separate limits that will be multiplying by each other because these 2 expressions are multiplying. So we'll have the limit as x approaches 0 of cos of 5x minus 1 over 5x, like that, times the limit as x approaches 0 of 1 over x, like that. Now notice that this here this limit, if we write it cos of 5x minus 1 over 5x, notice that it's in this format now for that second property. So if I do a change of variable, theta equals 5x, notice how as x approaches 0, theta approaches 0 as well. So this would end up being limit as x approaches, or theta approaches 0 after we do the change of variable of cos of theta minus 1 over theta. It's now in that format, and that's equal to 0. So this bracket here is going to equal to 0. We just showed that work. However, here is where the problem is with this method, this limit. Notice that this limit, the limit as x approaches 0 of 1 over x, does not exist. It is undefined. 1 over x, we know that's the parent rational function. It looks like this. So as we're approaching 0, what are the y values approaching? Well, from the left side, they're approaching negative infinity, and from the right side, they're approaching positive infinity. So they're approaching two different values. And so this here, this limit, does not exist. And because this limit does not exist, we cannot just take 5 over 7 and then 0 multiply it by something that doesn't exist. It's not going to show us that this limit is going towards something. It also doesn't prove to us that this overall limit doesn't exist. And hence why this method of trying to use this property, even though, again, it's really deceiving because it looks like it's in that format, this cos of 5x minus 1, even when we try to use it, we're not going to be able to solve this limit just because of this part here. So we actually have to use a different strategy. And here's where it's going to be a little unique. You haven't seen this strategy yet. You've seen it actually back in advanced functions and grade 11 functions when we did trig identities. I don't know if you remember, but sometimes we would have trig identities where we would have like a cos x minus 1 in the numerator or denominator, or sometimes even a sin x minus 1, or even a sin x plus 1. And what we had to do was we had to multiply this by its conjugate, cos x plus 1. But then we had to multiply the other fraction by that as well, the other side of the fraction. So we would be multiplying that expression by 1. And the reason why we did that is because then we'd end up with cos squared x minus 1, which could become 1 minus cos squared x, which could then become sin squared x. Because if you remember, sin squared x plus cos squared x is equal to 1. And it doesn't just have to be an x. We can have sin squared of an expression plus cos squared of an expression, of that same expression, is equal to 1. And then we can mix and match this. So we can say sin squared, if we isolate for the sin squared of an expression is equal to 1 minus cos squared of that expression. Or sin squared x equals 1 minus cos squared x. And this is actually what we're going to have to use here. Okay, so it's a little weird, but what we actually got to do is we got to take this and multiply it by the conjugate of cos of 5x minus 1. So we would multiply it by cos of 5x plus 1. But then we can't just multiply the numerator by cos of 5x plus 1, add this random expression. So we've got to multiply the denominator by the same thing. So it's like we're multiplying this by 1. So we're keeping this the same, just adding more onto it. So now what's going to happen? Well, we're going to end up having the limit as x approaches 0. When you multiply a two-term expression by its conjugate, you're just going to multiply the ends. So we're going to have cos of squared of 5x, cos squared 5x, this times that. Negative 1 times positive 1 is just minus 1, like that. All over These two I'm going to keep separate. So I'm going to have 7x squared, and then I'm going to have cos of 5x plus 1, like that. Right? So I know it's a little confusing, but we basically had to rationalize this first, multiplying it by this conjugate over that conjugate. Okay, so very similar, if you remember again, to some trig identities that we had to do. So from here, remember we had sine squared of an expression is equal to 1 minus cos squared of that expression. But we have cos squared of that expression minus 1. So to get into that 1 minus format, we actually have to factor out a negative here. So we'd have the limit as x approaches 0 of negative, and now this would become 1 minus cos squared 5x, like that, over, let's keep that denominator the same as is. Right, so I told you this would be pretty unique. Hopefully you're still with me with what I am doing. And now, I actually erased it. Let me just bring it back. Remember, sine squared of an expression is equal to 1 minus cos squared of that same expression. So notice that if I put 5x here, 1 minus cos squared of 5x is equal to sine squared of 5x. So this bracket here is actually equal to sine squared of 5x. And we want to make that substitution here. And then from there, we can actually start making this limit in a certain format where we're going to be able to use the first property, this property here. So I'm going to show you how we do that. But the point is that after doing all this manipulation using this method, we're not going to be using the second property, we're going to be using the first property. So I'm going to show you in a sec how that works. Now, I'm going to plug in this sine squared 5x here for this bracket, but at the same time, I'm also going to factor out some constants. So I'm going to take out this -1 and then this 7. So I'm going to have -1 over 7, taking those constants out. Then I'll have the limit as x approaches 0. This bracket becomes sine squared 5x over, we're going to have an x squared left, and then we're going to have this other entire expression, cos of 5x plus 1, like that. Okay, now another thing, remember that sine squared of 5x, that's the same as sine of 5x times the sine of 5x, like that. So that's what I'm actually going to do just to show you how we're going to split out this limit. So this sine squared 5x, I'm going to rewrite like this. So I'm going to have sine of 5x, sine of 5x, all over this x squared, I'm actually going to rewrite as x times x, and then cos of 5x plus 1, like that. Right? The reason why I want to split these up here is because we're going to be creating separate expressions, so I just want you to see more clearly where everything is coming from. So if I continue this, I'll actually continue it up here. May need more room. So if I continue this up here, erase all of this, we would end up with that -1 over 7 outside of the limit. We'll have the limit as x approaches 0, and now I'm going to create a bunch of expressions that are going to multiply by each other. So I'm going to take this first sine 5x and put it over this x here. So I'm going to go sine of 5x over x, like that. I'm going to take this sine 5x, put it over this x. It's going to be the exact same expression, like that. And then this cos 5x plus 1 still remaining in the denominator, so I'm going to put 1 over that. So we'll have 1 over cos of 5x plus 1. So inside this limit now, we're multiplying by 3 expressions. And actually, these two are the exact same, so you could combine them and have it squared. I'm just going to keep them separate like this, but you can also combine them if you want. So from here, what I'm going to do is I'm actually going to use the limit law, where whenever we're multiplying expressions inside a limit, we can make each of those expressions their own limit. So notice there's 3 expressions here, so I'm going to make 3 limits. So I'm going to have the limit as x approaches 0 of sine of 5x over x. Now, if you squared these two, if these two were squared, you can actually take this limit here and then square it. That's a limit law you can use as well. It will actually probably look nicer, to be honest, to do it this way. But just because we've split them up, I'm going to just multiply those 2 limits. But you can also do it that way that I just showed you. And then whatever result you end up getting for that limit, you would just square that result. But I'm going to keep the 2 expressions separate like that. So this and that, 2 separate limits. And then we got the limit as x approaches 0 of 1 over cos of 5x plus 1, like that. And now what we do is we're going to work with each of these limits separately. So starting with this one, we got the limit as x approaches 0 of sine of 5x over x. Now notice that this here, there's like a 1 in front. It's actually in this format. So the m is the 5, the n is the 1. So we know that this is going to end up being m over n. We did a video before where we showed that result in more detail. So this ended up being 5 over 1 equals 5. If you do want to show your work quickly with this, what we want to do is try to use this fundamental property. So we got to make this expression also be in the denominator. So we got to multiply the denominator by 5, meaning we got to multiply the top by 5 as well. Okay, you can't just multiply a 5 in randomly into the denominator. If we do, we got to multiply the numerator by 5 as well. So what I'm going to do is I'm going to take this 5, take it out of this limit as a constant, but then this 5, I'm going to put here with this x, like that. Do a change of variable, theta equals 5x. As x approaches 0, theta is going to approach 0 as well. So we'll have 5 times the limit as theta approaches 0 of sine of theta over theta. And now notice that this is equal to that. So we'll have 5 times 1, which is equal to 5, which is the same answer that we got when I mentioned this result that we got in a previous video. But if you want to show your work, that's how you show it quickly, right? So this limit, we just showed how it equals 5, meaning that this limit also equals 5. So we'll end up having negative 1 over 7 times 5 times 5, this. Notice here, what can we do? We can do a direct substitution, because when we plug in 0 for this x, the denominator won't be 0. We would end up with 1 over cos of 5 times 0 is 0 plus 1. So we'd end up with 1 over 1 plus 1, right? Cos of 0 is just 1. So this would end up being 1 over 2, this bracket, after we do a direct substitution. So this ends up being 1 over 2, this bracket. And now when we multiply everything, this 5 is over 1, this 5 is over 1, so we'd end up with negative 25 over 14. And that ends up being the answer to that initial limit that we had. And that initial limit was the limit as x approaches 0 of cos of 5x minus 1 over 7x squared. So again, this one, in my opinion, was tough because initially looking at it, because of this expression cos of 5x minus 1, it looks very similar to that. So initially looking at it, you would think that we're going to be using this property. But as I showed, when you try to manipulate this to be able to use that property, you end up running into that roadblock of the limit as x approaching 0 of 1 over x not existing. So we actually don't use this property. We got to take this, got to multiply by the conjugate of the numerator. So cos of 5x plus 1, multiply the denominator by that as well. And then you end up with a totally new expression, split it up into a bunch of expressions, and we actually end up using this first property instead. Right? So in my opinion, a pretty tricky one. And I actually recommend that instead of using actual numbers 5 and 7 here, you can try to put a general term m and then a general term n, where m and n are any real number. And I would actually try to work this limit here and come up with a general expression using the same method that we did. And your final answer should be negative m squared over 2n. Right? That would be the final answer. So I'd recommend trying it. Try to challenge yourself. If you don't end up getting this, I'm sure you will if you follow the same steps. But if you do want a written solution from how to get to this general limit, to this general expression, just let me know and I'll send you the written solution. But try it yourself, try to get to that. And notice that for the limit that we did, this corresponds to this answer. Because notice how that m was 5 for our limit that we just did, and then this n was 7. Plugging in the 5 and 7 here, we'll have 5 squared, which is 25, then times that negative. Remember, you got to do the exponent first and then multiply by the negative, BEDMAS. So negative 25, and then 2 times 7 is 14. So this ends up corresponding to that general term. So again, I'd recommend trying it just for extra practice. But yeah, you got to be careful with these kinds of limits. Sometimes you may have to multiply by the conjugate. So it's pretty tricky. Be on the lookout for those.